Hi there. You're very welcome to today's lecture on significant figures. I'm your very own personal physics tutor, Dr. Rima McMullen. In today's lecture, we are going to look at the difference between two very closely related but different terms, accuracy and precision. And then we are going to look at the different rules to tell how many number of significant digits are there in a given number. Alright, so let's see. So you might ask, what's the significance of significant figures, also called as significant figs or significant digits? Now, significant figures, these are essential in expressing the precision of measurements in scientific calculations. Big words, what do they mean? Now, you know that science is an experiment-based subject. That means in science you do experiments. And when you do experiments, you're measuring some quantities. And when you measure those quantities, you get some data. And this data will have some accuracy and some precision based on the tools that you're using, and of course based on the attention to details of the person, whoever is performing the experiment. Let's say whoever is performing the experiment is a very careful experimenter. So now the accuracy and the precision of the data depends on the tool used. Let's look at the difference between accuracy and precision. So for accuracy, you can say that the closer the measurements, the individual measurements are to the expected, or you can say theoretical or the actual value of the quantity that you're measuring, the more accurate your measurements are. Maybe it didn't make much sense yet. Let's look at an example to make sense. Consider an example to understand the difference between precision and accuracy. Let's say an experiment is being performed to measure the value of g, the acceleration due to gravity near the surface of Earth. Now we know that the value of the acceleration due to gravity near the surface of Earth is 9.81 meters per second square. Let this experiment be performed independently by Bob and by Sam. And we are going to compare the data of Bob and Sam. Let's say Bob does 3 trials and he measures the value of g to be 9.62 meters per second square in his first trial, 9.83 meters per second square in his second trial, and 10.03 meters per second square in his third trial. We're going to look at the average value of these 3 trials, and that average is 9.82 meters per second square. So if you look at the average value, it is fairly close to the 9.81, which is the actual value. So Bob's experiment has high accuracy. Why? Because his average value is very close to the actual value of 9.81. However, if you look at the individual data points that are shown here in blue color, you can see that these data points are quite widely separated from each other. So I would say that this has low precision but high accuracy. Let's next look at Sam's data. So Sam's first value G1 is 10.02 meters per second square. G2, it's 10.05 meters per second square. G3, 10.03 meters per second square. This gives the average value to be 10.0333 meters per second square. Now this average value of 10.03 meters per second square, it's not very close to 9.81 meters per second square. So you will say that Sam's data is not very accurate. It has low accuracy. However, since these 3 values, these are not too far from each other, you will say that the data is highly precise. High precision, low accuracy. So Bob's data, where the average value was close to the actual value of 9.81, that had high accuracy. However, since the individual data points, these are widely separated from each other, it had low precision. On the other hand, Sam's data, where the individual data points are very close to each other, it has high degree of precision But since the average value of G is not very close to the actual value of G, which is 9.81, it has low accuracy. Let's look at one more example to understand this better. Next, we're going to look at this target-making game between 4 players A, B, C, and D. Player A, he throws his darts and they land 1, 2, 3, and 4. Player B, he throws his darts and they land 1, 2, 3, and 4. Player C, he throws his darts 1, 2, 3, 4. Player D, his darts go 1, 2, 3, and 4. Now player A, if you take the average of these 4 darts, where would it land? It would land here in the middle. Do you agree? The average of the 4 pink-colored crosses, they should land here right at the center. So you will say that for player A, he has very high accuracy. But what would you say about his precision? Are his 4 darts close to each other? No, they're all over the place. So this player A will have low precision. Do you get it? Player B, his darts are fairly close to each other. So you will say that this player has high precision. What would you say about player B's accuracy? The average of these 4 darts will be somewhere over here, right? Here. And it's not very close to the center. So this one will have poor accuracy. All right, that's didn't seem like accuracy. Player C, where do you think the average would be? I would say the average would probably be somewhere over here. Over here. So yeah, it's kind of, not too far from the target, but still it's not very accurate. Kind of, moderate accuracy. But if you talk about precision, this one has low precision. Last, but not the least, player D. Now his average is going to be pretty close to the actual target. Do you agree with me? I think the average will be somewhere over here. So this guy, D, he has high precision. Why? Because the values are very close to each other and also high accuracy. That's because his average for the 4 darts is very close to the target. So I hope that this illustrates the difference between accuracy and precision. Now that you hopefully understand the difference between precision and accuracy, we're going to move on to the rules of identifying the number of significant digits in a given number. So let's look at rule number 1. Rule number 1. All non-zero digits are significant. Examples: 234, 3 sig figs. 7892, 4 sig figs. 921473, 6 sig figs. Very good. So here's a question for you. How many sig figs does 1092 have? So here we know that 192, these are non-zero digits, so therefore it has at least 3 sig figs. But how about this 0 right here? To answer this question, we're going to look at captive zeros. So captive zeros, these are zeros between non-zero digits. For example, we said 1092. This 0 here, it is between 1 and 9, and 1 and 9 are non-zero digits. So this 0 here, this is called as captive 0. This is held captive between 1 and 9. All right. Next, all captive zeros are significant. Let's look at some examples. 1092. This 0 over here, this is captive 0. And rule number 2 is saying that all captive zeros, that is zeros in between two non-zero digits, they are significant. So how many sig figs are here? 1, 2, 3, and 4. So there are 4 sig figs. Very good. Next, 230092. These zeros between 3 and 9, these are captive zeros, and therefore these are significant. So this number has 230092. Total of 6 sig figs. 50100053. So this zero and these two zeros, these are captive zeros because these are in between non-zero digits. So this number has 1, 2, 3, 4, 5, 6, 7. 7 sig figs. Now you might ask why I'm drawing these lines over here. It just helps me keep track of the digits. These are big numbers, so I lose track of things easily. Next question. How many sig figs does number 0.00234 have? Now these zeros, are these captive zeros? No, because these are not in between any two non-zero digits. These are to the left of the first non-zero digit. Okay, so what do you think about this? Are these zeros significant or not? To understand this, let's look at an example. In this example, let's say we want to measure the bottom length of this box over here. Using this ruler, we find the length to be 1.6 centimeter. Well, it's slightly smaller than 1.6 centimeter, but just for the sake of it, let's call it 1.6 centimeters. Let's say we're asked to specify this length in meters instead of centimeters. So for that, what I do is I divide this by 100 and it becomes meters. And this can be written as 610. So this is 0.016 meters. Okay, so if I look at 1.6 centimeters, here it had 2 sig figs, right? Because 1 and 6 are both non-zero digits. Now just because I changed my unit of measurement from centimeters to meters, the significant figures should not change. The number of sig figs when I was using the unit centimeters should be the same as the number of sig figs when my unit of measurement is meters. That means these zeros over here, they are not significant. Do you see the point here? So all I have done is I've changed the unit of measurement from centimeters to meters. By doing so, I'm introducing these zeros to the left of the first non-zero digit. And just because I have changed my unit of measurement should not impact the number of sig figs in my measurement. So from here, it is very clear that the zeros to the left of the first non-zero digit, they are not significant. Alrighty? So let's go back to that. Rule number 3 is leading zeros are not significant. So what are these leading zeros? These are zeros to the left of the first non-zero digit. Example, 0.00538. These zeros here, these are to the left of the first non-zero digit, which is 5. So these zeros are non-significant. They are not significant. How many sig figs are here? 5, 3, and 8, which are 3. 3 sig figs. Fairly easy so far, huh? Next one, 0.0050038. So we know that these leading zeros, these are not significant. But how about these two zeros in the middle? These are between 5 and 3. What do we call these zeros? As per rule number 2, these are captive zeros and hence they are significant. So how many sig figs are here? 1, 2, 3, 4, 5. There are 5 significant digits or figures here. Okay. 0.000035829057. Let's scratch out these initial zeros. These leading zeros are not significant. And then we have 1, 2, 3, 4, 5, 6, 7, 8. 8 significant digits in this number. So there it is. Leading zeros are not significant. That's our rule number 3. Rule number 2 was captive zeros are significant. And rule number 1 was all non-zero digits are significant. So it's easy. The rules are actually very easy. So here's the next question for you. How many sig figs does 12,000 have? Now these 3 zeros, these are at the end of the number. These are not leading zeros. These are not captive zeros. These are what we call as trailing zeros. So what's the rule for trailing zeros? Let's look at that. Rule number 4 is that the trailing zeros in whole numbers are not significant. So here the key word is whole numbers and trailing zeros not significant. Let's look at some examples. 50 million. So here all of these zeros, these are trailing zeros. Why? Because these are to the right of the last non-zero digit in a whole number. So all the zeros that are to the right of the last non-zero digit of a number, which is a whole number, they're called as trailing zeros, and these trailing zeros are not significant. So none of these zeros are significant. There's only one significant digit here in 50 million, and that is 5. Next example, we have a huge number, 20 billion, 2002 million. So here we have 6 trailing zeros. So these are trailing zeros, not significant. Then we have this zero and these 2 zeros. These are all captive zeros, and captive zeros are significant. So how many significant digits are here in this number? 1, 2, 3, 4, 5, 6. 6 significant digits. All right. A question for you. How many sig figs does 21.20300 have? So what's different about this number? This number has a decimal and there are non-zero digits to the left of the decimal. Unlike we saw in problem number, unlike the numbers like this 0.002, where we had these leading zeros and we knew that these leading zeros were non-significant. Right? But here we do not have any leading zeros. However, we have zeros at the end here. So what do you think? How many significant digits would it have? Example of trailing zeros. So 21.20200. These zeros, these are trailing zeros and they're to the right of a decimal point. So these zeros are going to be significant. And this zero over here, this is a captive zero, and therefore this zero is also significant. So how many significant digits do we have in this number? 1, 2, 3, 4, 5, 6, 7. 7 significant digits. Next we have 38.093200. Again, these are trailing zeros to the right of a decimal point and therefore significant. And this zero over here, it's captive zero and is significant. So this number has 1, 2, 3, 4, 5, 6, 7, 8. Okay, I lost count. 1, 2, 3, 4, 5, 6, 7, 8. 8 significant digits. Easy breezy so far? Huh. Next we have, here we go, these 3 are trailing zeros, right? And therefore significant. These trailing zeros are to the right of this decimal and therefore significant. These two zeros, they are between 8 and 3. These are captive zeros and are significant. However, these zero here, these leading zeros, they are not significant. So these three are not significant. What are we left with? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. Whopping 10 significant digits here. So in early 1900s, the scientists thought that physics was pretty much done. All they had to do was whatever known quantities were, they needed to be measured to higher number of significant digits. They were quite wrong. Quantum mechanics came after that, and so did general theory of relativity. And they revolutionized physics, and we believe physics isn't done yet. There's a whole new, totally uncovered physics that still remains to be uncovered. Maybe you will be one of them who will do that. We'll see. Here's a question for you. There are 4 employees at the XYZ grocery store. How many significant figures are there in the number of the employees for the store XYZ? That's 4. We know that it's exactly 4 number of employees. I mean, could you have 3.5 employees? Well, maybe you could. If you were doing, if somebody was doing part-time job, half-time job, but even then we'll know precisely that there are 3.5 number of people working. That means 3 people are working full-time and 1 person is working half-time maybe. Or maybe 7 people are working half-time each. But in any way, you will know exactly how many number of people are working. So you will say that for such cases, these numbers are called as exact numbers. So the rule for exact numbers are exact numbers, that is the numbers that are counted, have an infinite number of significant figures. For example, I might say that I have 10 pens. What's the number of significant figures in the number of pens I have? Infinite. I know it to infinite certainty that I have 10 pens. Maybe I have 15 books on my bookshelf. Infinite number of significant figures in this number 15 because this is an exact number. Okay? Recap of the rules of significant figures. All non-zero digits are significant. For example, 324. There are 3 sig figs. 5, 2, 8, 9, 2, 3. There are 6 sig figs. So all the non-zero digits, they are significant. Rule number 2. All captive zeros are significant. Captive zero are zeros between 2 non-zero digits. For example, 202. It has 1 captive zero, which is in between the 2 2's. So this will have 202. It has 3 significant figures. 3006. There are 2 captive zeros. And 3006 has 4 significant figures. 202002. There are how many captive zeros here? 3. And total number of sig figs? 1, 2, 3, 4, 5, 6, 7. 7 sig figs here. Rule number 3. Leading zeros are not significant. Leading zeros are, like for example, 0.0034. These zeros are to the left of the first non-zero digit. And these are not significant. So the 3 zeros in 0.0034, they are not significant, but the 2 non-zero digits, which are 3 and 4, they are significant. So there are only 2 sig figs here in 0.0034. Trailing zeros in whole numbers are not significant. For example, 420. There's a 0 at the end of this. This 0 is not significant. Okay? And 39000, so 39,000. 39,000 has 3 zeros at the end. Those are called as trailing zeros. So this trailing zeros in whole numbers, this whole numbers is the key word here. So 420 has 2 sig figs and 39,000 also has 2 sig figs. Then we have trailing zeros at the end and to the right of a decimal point are significant. For example, 3.100. There are 2 zeros that are to the right of a decimal point and they are at the end of the number. So these are trailing zeros but not in a whole number. So these trailing zeros that are not in a whole number, they are significant. So if I had 3100, then these zeros will not be significant. Why? Because 3100 is a whole number. But when I have 3.100, in this case I have these zeros at the end, these are significant. And I have how many sig figs? 4 sig figs. Next one, we have exact numbers have an infinite number of significant figures. So if I say that I bought this pen 3 days ago, then those 3 days, this is an exact number. And therefore, 3 days has an infinite number of significant figures in it. So any number that is exact, I drank 2 liters of water, which I do on most days, then that 2 liters has an infinite number of significant digits in it. So I hope that by now you understand these rules to identify how many number of sig figs are there in a given number. And using these rules, we'll learn the operations like multiplication, addition, division, subtraction in the next lecture, which is very, very important. However, before we move on to next lecture, I have a little quiz for you on the next slide. So here's a little quiz for you guys. You're asked to identify how many number of sig figs or sig digits are there in each of the following given numbers. So my recommendation to you is you should pause this video and answer these questions on your own and then come back to check your answers. Okay? All right. So I hope that you have solved these on your own and now you're back to check your answers. Number 1, 2, 3, 4. They're all non-zero digits. So there are 3 sig figs. 2.34. Although there is a decimal, but there are 3 sig figs here because there are 3 non-zero digits. 2034. Now there are 3 non-zero digits, 2, 3, and 4, which are same as in 1 and 2. But there is a 0 here, which is a captive 0. So captive zeros are between 2 non-zero digits, and non-zero digits are always significant. So this 0, the captive 0, is also a significant digit. There are 4 significant digits or figures in number 3. Then we have 203400. We know that 2, the 0 that is between 2 and 3, which is this one, the captive 0 is also significant. 4 is significant because it's non-zero. But these zeros, the trailing zeros at the end of a whole number, these are not significant. So 203400, this will also have 4 significant digits. Why? Because the 2 trailing zeros are not significant. Number 5. Now this one has 2 leading zeros, and leading zeros are never significant. So if you take out the leading zeros, then we're left with 2034, and therefore it has 4 significant digits. Number 6. Now for number 6, we have 2 leading zeros, which are non-significant. Then we have 1 captive 0, which is significant. And we have 3 trailing zeros. Now these 3 trailing zeros, these are to the right of a decimal. And therefore, these trailing zeros are now significant. So how many significant digits are there? 1, 2, 3, 4, 5, 6, and 7. 7 significant digits. Number 7. 5045020. So it's 5,045,020. All right. This is a whole number, trailing zeros for the whole number. That is the zeros at the end of the number. They are non-significant. So I took out that 0. The 2 remaining zeros in this number, they're captive zeros and therefore are significant. So Now we are left with here 6 significant digits. Easy, right? It is. Number 8. Earth has only one natural satellite, which is Moon. How many sig figs are there in the number of the natural satellites that Earth has? Infinite. Why? Because Earth has exactly one natural satellite, which is its Moon. So it has infinite number of significant figures or digits in the number of the natural satellites that Earth has. Cool. So that was your lecture on significant digits. How do you identify how many number of significant figures or significant digits are there in a given number? And we also looked at the difference between precision and accuracy. So in the next lecture, we're going to discuss when you perform mathematical calculations on some data, on some measurements, then how do the rules of significant figures, they propagate into those calculations. Okay? And we're also going to talk about scientific notation. When you write a number in scientific notation, it makes it very easy to tell how many number of significant digits are there. So those things will be discussed in the next couple of lectures, which will then be followed by measurements and error analysis and measurement. Okay, and if you haven't done so yet, please subscribe the channel and like the video. It will motivate me a lot to make more videos for you. I'll see you again very soon on the next lecture on scientific notation and significant figures, and the lecture after that will be propagation of significant figures in mathematical operations. After that, the next lectures will be on the propagation of error and error analysis and measurements. Alrighty.